In this video, we're going to talk about our cable tester product. Now, our lab, like pretty much every other lab that does storage and networking, has a box of suspect cables. In here, I have a bunch of cables, all look exactly the same. They have the same ends. Some of these cables are SAS, which are 100 ohms. Some of these cables are PCIe, which is 85 ohms. Some of them are 6 gig, some of them are 12 gig. Some of them are Gen 5, some are Gen 4. A lot of them are broken. So what do we do with these? Well, normally you go and find a new one because it's too much effort. The Quartz cable testers is designed to solve that problem. So, Andy, perhaps you'd like to tell me a little more about this cable.
Right, well, I don't know very much about it yet. Let's find out. So this is our MTIO cable tester. So it's very simple to use in its basic form. We turn it on, plug it in, plug the cable, loop back into each end. Lights flashing to show it's working. So what this is going to do, it's going to identify the cable. It's going to read the EPROMs on both sides, work out what speed the cable is compatible with. It is going to run a high-speed compliance pattern through the cable, check all the lanes are mapped in the correct way, check there's no errors, and hopefully light's gone green. This is a good cable.
So the cables, the box has decided that all 4 lanes are running at the correct speed.
At full speed with no errors.
And that both ends of the cable have the correct EPROM and that they match.
Correct. So we got a very good way to say that we took this cable and put it into our test system. It's going to work. It's going to do what we want. But we can see a lot more than that in the application as well. So we can simply connect this up on USB or Ethernet. We can open up the Cable Test Studio and we can ask the system to tell us more about this cable. So have a little look at what it actually is. So this is our QSFP cable tester. So the cable's now installed. Now we saw it went green before, but now I can connect to this device over USB, in this case in the application. And I can see here we've passed our EPROM test. We found the EPROM, we've passed mapping the cable to check that all the links are in the correct order. We passed training, where we have trained our transceivers against this cable. We have run a synthetic eye diagram, and we've run a bit error rate test. All of those are green, all the links are good. We can go through and we can look at the mapping and see we've got one-to-one mapping. Everything's connected up as we'd expect. The eye diagrams are looking nice, clean, consistent, even. The eyes wide open suggests that this cable is going to, even if we add a bit more into the signal path, maybe plug it into a system that has adapters in it, it's hopefully going to run cleanly. Again, we can look at the EPROM. We can confirm that this is a QSFP28 cable. So for Ethernet, it's spec to run at 25.7 gig. We can see the vendor serial number, the date of manufacture, product codes and similar. All this looks good. So let's try another one, shall we? Let's unplug this cable, and we've got this one's an optical cable. Look, exactly the same thing should apply. We can test optical cables as well, because what we're really interested in is the quality of the end-to-end communication. It doesn't really matter to us what's in the middle. We're testing the entire circuit. So the test is running automatically there. We'll start to map the cable. And just give it a few seconds. Mapping's passed.
And what does mapping do?
So mapping, we are basically trying to work out which lane is connected to which. There are 4 different high-speed lanes in here. A cable like this, especially a copper cable, they could be crossed over, or some of them could just be not connected at all. So we can tell if they're not connected. We can tell if they're unusually wired. Now this cable is not happy. We have failed to calculate the eye heights for several of the links. Some of them are running error-free, some of them are not running at all. So let's look at the details of this cable. So the mapping looks good. We're one-to-one mapped in all of the lanes, that's fine. You see we've got eye height failures in some of these, so we'll check the mapping. It's all good. We've got one-to-one links to the mapping. All looks like we'd expect for the cable. Take a look. Ooh, right. Eye diagrams are horrible. So we've got very small eyes. This is very different to what we saw in the previous one, and this is what's going on here. Now, it may be a problem in the optical side. Perhaps the cable's dirty. Perhaps there's something damaged on one of the connectors, but this cable is not working correctly. And from the eye diagrams, we can immediately see that all the lanes are very poor. Something's gone very wrong here. On the EPROM side, everything's looking fine. We've identified the speed of the cable. We've identified who manufactured it, what the part number was, the serial number and similar. But this cable should be either needs repaired or in the bin, one way or the other. Shouldn't even be in the suspect cables box. So this is QSFP. We've got another version here. So this is for Mini SAS HD. This is a slightly older model. This new one is designed with removable front panels, so we can switch over and test different types of cables. We could just change over here.
Yeah. The other advantage of being able to replace the front panel is we can replace the connectors when they wear out.
So let's just connect in another cable. Again, test start automatically. We've identified the cable and can begin testing immediately. So we don't need the software, but it does tell us a lot more, which can be very useful. Okay, so this is an 8 gig cable. So this is quite a bit slower. Now that does mean it's going to take longer to test. So because we have the same target error rate for the cable, which is, I believe, 1 times 10 to the minus 12 bit error rate, we have to run what we
1 times 10 to the minus 12, 10 to 12 bits.
That's a lot of bits. And the slower the rate of the cable, the longer that's going to take. So a cable like this, okay, it's just completed, fully passed. So this is a serial cables Gen 4 PCIe cable by the looks of it. It's running perfectly. There's no errors. It's clean. The mapping looks correct. The eye diagrams look excellent. Now that's not surprising. It's a lower speed. We're running at 8 gig now, not 25.7 gig. It's going to be easier to get the signals down the cable. But this cable looks great. We can take that one out the suspect box and we can put that back into the lab again. This is very much usable. And get one more cable. This is a longer one. So a longer signal path does mean that it's a bit harder to get the signal down the cable. Maybe the quality won't be quite as good. Now this one, we've got an EEPROM decode warning. That's interesting. So it's struggling to work out the speed of this cable. We can't work out the protocol of the speed of the cable. Now, it could be because the connector is damaged. We're not talking to the EEPROM correctly, but we have been able to pull out the vendor name, part number, and date code. So that suggests that the EEPROM on this isn't actually encoding the cable speed.
So you're saying that the EEPROM in this cable does not meet the standard, and therefore may not be read by...
Exactly. Now, if you put this in many systems, they're not going to care because they won't read the EEPROM and it'll work. But that won't necessarily stay that way. I mean, what if someone upgrades the server later, it starts looking at the cable to work out what speed it is, it might fall back to a lower rate at some time in the future, and then how on earth are you going to debug why your whole data center or your server has slowed significantly, all because of a cable that doesn't identify itself correctly? Other than that, the cable looks fine. Now, because we haven't been able to work out the speed, we are testing it at a lower speed, but the eye diagrams look good. It is running error-free. It's not bad for data. It's just not identified nicely. So we clearly have got work to do. We need to go through all these cables here. We need to check which ones are good, make sure that we only have cables that are identified correctly and running error-free in our lab. The rest, we either need to label them or ideally just cut them in half. Now, these are expensive things as well. I mean, cables can run anywhere from $50 to several $100. It can be very worth having a tester like this in your lab to ensure that good cables can go back into use again and that poor ones are removed before they cause problems in setups.